right, so this is a presentation that I have given at the Science Festival here in Minsk like half a year ago. It was quite a lot of fun there, but it also means that it's like you probably wouldn't understand some of the memes, you know, that I used. Like if you're not wasting your lifetime and your mental health, you know, sitting on the Russian internet as I do. But anyway, I didn't bother translating.
It'll be interesting seeing it from the other side. Yeah.
Yeah. Okay. And the very name for it, it's like an old joke in Russian, like I'm not Copenhagen, which means like, well, it means kind of I'm not competent, you know, but you know,
oh, okay.
Sort of a fun, yeah.
I thought you were referring to like Ito or something.
No.
No, but it's too far off.
Ito
well, and from our standpoint, it's like they're almost the same place, you know. Like
yeah, okay. Well, it definitely relates to, you know, Copenhagen interpretation, so
okay.
That's why I put it that way. All right, so. Yeah, so just a small organizational note. I believe, like, if you would have questions that kind of immediately relate to what I'm talking about, like if you don't understand what I'm saying, I propose to ask them right away, questions or comments or whatever, because, well, it's quite a complex subject. So if you kind of get lost somewhere, it might be, you know, harder to understand what I'm going to be talking about later. So, but if you have some sort of, you know, more general philosophical questions or comments, they're better to be left, you know, towards the end, because we might go really far with that, obviously. Okay, so, yeah, somehow it doesn't work. Okay, yeah, so what I'm going to be talking about here, it's the first part is going to be like motivational part, like why the hell should we be interested in this topic in the first place? Then I'll give you some like basic description of how quantum mechanics perceives the world. And it's going to be sort of perhaps a bit different from what you can read in textbooks or something. So this whole presentation is kind of my vision of it. So, you know, I would do some characterizations that perhaps you wouldn't even find anywhere else, but, well, hopefully it would help you understand the subject. Then I'll talk about some paradoxes, which is, you know, quantum mechanics is pretty famous for having those, which I believe kind of represents some unanswered questions about, you know, our worldview and so on. And then I'll list a few of the most popular interpretations of quantum mechanics, which are essentially, I would say, like attempts at getting answers to these questions, these paradoxes and so on. And then I'll just add a few points for discussion, because there's really a lot to talk about. And this whole presentation is, its goal is just to give you a like very rough understanding of it. So obviously I would be omitting many, you know, technical points and so on. It's really just a, you know, wide stroke, so to speak. Okay, so it's pretty much the kind of explanation that you would get again in some textbooks or whatever, that like at the beginning of 20th century we had some problems in physics. I'll list them on the next slide. And then quantum mechanics appeared that supposedly solved these problems, right? And from quantum mechanics, we were also able to derive some practical applications, some devices, and so on. But so here we're going to be dealing with this part, right? And we'll hopefully I'll be able to show you that it's not very bright right here, that there are many issues that exist. Yeah. So, but yeah, but first I want to address this thing, because that way or another, at some point here, you would have a question, why? Like, why do we need all that, you know, because it's really kind of stupid and complicated. So let's take a look at applications first to kind of understand that it's not just, you know, some very abstract theory, but it has real world consequences, so to speak. So one of the most prominent fields where quantum mechanics is applied is semiconductor technology, you know, speaking about new diodes, transistors, and things like that. You probably know that like early electronics was based on vacuum tubes, but it was, I mean, they're pretty big, you know, and then the like performance is pretty low in the sense of, you know, the speed. So you cannot say build a decently sized, powerful computer with vacuum tubes, right? So you need this much smaller devices, which are currently based on semiconductors. So we can, in a way, we can say that our warm and fuzzy tube girls were, you know, substituted with cold cat girls, essentially.
That's
all right,
over
so
here too.
Another, yeah, and you know, well, it's actually like in many areas, vacuum tubes are still like the preferred choice, like, you know, guitar amplifiers and things like that, because supposedly they give you this more what is called warm sound.
Right.
You know?
Right.
But still, you know, I mean, all the computers work on semiconductors, and you need quantum mechanics to kind of properly describe like the energy levels, you know, and things like that in semiconductors. Then other very prominent field of application of quantum mechanics is lasers. Now, I can probably, I cannot even state like how important lasers are for our current society. Like there's so much technology kind of tied to that area. So I wouldn't even start doing that. But like the very idea of a laser, it's based on this quantum mechanical concept of levels of energy and things like that. Then obviously we have optics, and again, the whole idea of spectroscopy, it's also based on this quantum mechanical idea that, you know, the energy is quantized, so therefore we might distinguish elements looking at their emission or absorption spectra, and so on. Then a very interesting field is quantum chemistry. You know, maybe you've heard about the guy named Luca Turin. So he actually talks about how quantum chemistry might be applied in the field of pharmacy, or I'm sorry, not pharmacy, but like perfume production, because, well, it turns out, I think I've mentioned that on one of the previous reviews. I'm kind of getting deja vus right now. Yeah. So basically, what he's saying that is that it turns out that, well, okay, it seems that our nose actually works as almost like a quantum spectral analyzer, you know. So the smells that we feel, they depend on what kind of spectrum the molecules have. So you can theoretically use that, use the, you know, quantum chemistry approaches to calculate the spectrums of molecules and conclude from that what kind of smell would they have, and it's just a very interesting, you know, field of application. And we also have quantum computers and quantum cryptography. I'll talk about them a little bit in the later parts of this presentation, so I wouldn't focus on that right now. And there are probably many other areas which I kind of overlooked. So in other words, this thing seems to work, you know, and you have to deal with it somehow. I mean, if you're proposing some sort of alternative explanations for quantum phenomena, you would still have to explain why all these things work, you know. So it's a kind of a dangerous subject in that regard. Okay, so I've mentioned that there were some physical problems at the beginning of 20th century, and the problems directly related to quantum mechanics were laws of electromagnetic emission. You probably know that there were some like serious issues with the description of the emission spectrum, you know, the black body problem and so on, with ultraviolet catastrophe, like infrared divergences and so on. And we've had some problems describing photoelectric effect because it had this red boundary, so-called, where there exists an energy, like, or rather a frequency of light below which, like if you take light with lower frequency, it does not produce photoelectric effect anymore, regardless of how intense the light is. And so that was a big problem, how to explain that. And obviously we've had problems with the description of atomic structure. But then came at least these three guys, Planck, who proposed that the energy, or actually what we're dealing with is action, but it's kind of related to energy, that it changes in, you know, these jumps. So it changes discretely, and it allowed him to describe the emission, you know, the famous Planck formula for a black body, for which he got Nobel Prize some couple of decades later. Then we've had Einstein's works where he used this Planck's hypothesis to explain photoelectric effect, and he also got Nobel Prize afterwards. And then we've had Bohr's postulates on the atom, which, well, I wouldn't kind of go into more details about them, but they kind of seemingly explained, you know, the atomic structure. So he also got Nobel Prize for that. And then, like, a huge explosion followed from that, where, like, many very pronounced, very famous scientists worked on formulating, you know, mathematical apparatus of quantum mechanics. So, you know, people like Heisenberg, Dirac, Pauli, and so on and so forth. So it was quite a club right there. You know, some of our brightest minds worked on that problem. Yeah.
Okay.
So, and the reason why I'm kind of noting these guys, because, well, as I've said, I've given this presentation here in Minsk, and he actually he worked at St. Petersburg, and he was the supervisor of our scientist Fyodorov, who was the first doctor of science in physics and mathematics in Belarus, and he actually kind of founded the whole theoretical physics school here. He was a very original thinker. Like, his works in optics, for example, are pretty serious, where he proposed to describe optical phenomena with what he called coordinate-less approach. That is, you know, basically tensor calculus instead of these huge equations that are coordinate dependent. But I digress. I'm sorry. So, and yeah. By the way, my own supervisor was a student of Fyodorov. So kind of, yeah. So Falk kind of appears to be my kind of scientific grandfather, something to that effect. So yeah, speaking of, you know, kind of inheritance of ideas and things like that. So the development of this apparatus helped us to calculate some physical quantities, such as, again, for example, spectra of atoms and so on, and perform some, you know, experimental validation of the theory. But the problem remained that the behavior of quantum objects was significantly different with respect to the classical objects. And we'll see that later with some of these paradoxes. So in a way, I would say that we might kind of break down this black box of quantum mechanics into two parts, where we have a mathematical apparatus. This is the Schrodinger's equation, by the way, which is, you know, I would say that this is sort of like a technical part. But we also have this sort of humanities part, you know, which relates to understanding what we're dealing with here, right? And the thing is that this mathematical apparatus is actually what gives us all these applications, you know, because we can calculate stuff and so on and so forth. And here it's all, you know, very neat and shiny, and we're all very glad that we have that. But in this other part, we actually have large problems even to this day. Like our worldview is completely destroyed by the quantum mechanics, and we still have no idea like how to describe the world according to quantum mechanical principles. Like again, we're going to be talking about these multiple interpretations that are there. So it's a very problematic part of it. All right. So, but we'll start now from like the very basics. I'm going to try to show you how quantum mechanics actually perceives the world. So this is a quote that I really like by Feynman, that I think I can safely say that nobody understands quantum mechanics. And there is another interesting quote that I kind of like. Ludwig Boltzmann, who spent much of his life studying quantum mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study quantum mechanics. So, but actually I've kind of cheated, because this guy was talking about statistical mechanics, but Ehrenfest was actually working on quantum mechanics too, so it's kind of connected, I guess. All right, so this is probably the most important part that you should know about quantum mechanics, that the main concept there is the concept of quantum state. So, well, that's pretty much all there is. And to describe what kind of quantum state we have, people use these abstract objects, abstract state vectors, that live in this abstract Hilbert space. So it's all, in a way, it's all very imaginary, you know. But just symbolically, I would prefer to, you know, depict these state vectors as just, you know, regular vectors. So you can just say that a state vector is just like an arrow that points at some quantum state that your system is in. It's not exact, you know. I mean, mathematically speaking, this is rubbish, but you can use it to kind of remember this terminology and to kind of understand it. So I think in that regard, it is fruitful to see it that way. And we also have like a purely mathematical formulation of all that stuff. Like we have this Dirac notation. I'm pretty sure you've encountered that somewhere, where you have these, basically these, how do you call it, parentheses. They kind of show you that it is a state vector of some quantum system. But the other interesting thing, and this is just like a side note, we're not going to be talking about it a lot, is that physical quantities are substituted by operators that act on these state vectors. So in quantum mechanics, you would be dealing with these types of expressions where, you know, some operator acts on this state vector, and you have some physical quantity right here. So, but again, we're not going to be talking about this, but it's just so you know. Okay. So, and one of the important properties of state vectors is that there exists so-called principle of superposition, where if you have these two possible state vectors in your system, then their sum would also be a possible state vector. So this wicked contraption is also a possible state if these two are. And obviously, well, this third part is something which is like, it's a purely quantum thing. It does not exist in you know, classical physics. So, and it's one of the things that creates many of the problems that we're going to be talking about later. But it's just, I mean, the way it's formulated, it is the case. And other thing that we might note here is that these state vectors might not be well, they might be different, right? So in the sense that kind of, well, it's just, you know, the way I propose to kind of heuristically represent that, but we can say that some vectors might be longer than others, which would mean that this state has much weight, you know, in the whole distribution, like it's more probable than this one. But you still might have this superposition state anyways. All right. And another interesting thing is that so-called entangled states are possible, where basically if you have more than one object, let's say you have two particles, in that case, they might be in the so-called entangled state. And in particular, any type of interaction between these particles would inevitably create this entangled state, all right? And what that means technically is that there are correlations between the states of these separate particles. So in a way, the state of one particle would depend on the state of the other and vice versa. So that's why they're called entangled, because, they're kind of, kind of intertwined in a way, right? You cannot just separate them. So their states are no longer independent of each other. And you can kind of visually depict this like that. So you have one object with one set of quantum states, and you have another object with other set of quantum states. If you have interaction between these objects, you have this system where you have correlations between the states of these separate particles. So they could no longer be described independently. And to kind of briefly sum up this previous discussion, I would say that quantum mechanics deals with these abstract state vectors, and it completely ignores the usual space, and all the concepts associated with it. And that's probably the main reason why quantum mechanics cannot be reconciled with relativity theory, because relativity is all about space, whereas quantum mechanics kind of absolutely ignores it. So they use completely different languages, completely different sets of concepts, and therefore they're hard to reconcile, or probably even impossible. But this type of description, it's exactly what brings forth all these new effects and paradoxes that we're going to be talking about later. So yes, I've said that quantum state does not depend on like regular physical space, but it could be represented in it. And such representation is what is called a wave function. But again, this is only one of the possible representations. Like you can, for example, represent quantum states in a momentum space, or there are different pictures, the different kind of projections of these state vectors in different contexts. So this wave function is only a spatial representation of state vector. So why is it called a wave function? Well, because it looks like a wave, all right? So it's pretty straightforward. And the fact that it looks like a wave, it follows from Schrödinger's equation. And one important thing you should know about the equation, is that it doesn't really follow from anywhere. In a way, it is just postulated, and it seems to be correct, right? So it's only proven by experiments, but it's not fundamental in the sense that we don't know where it comes from. Like it's just introduced almost artificially. Well, there are some requirements that it should have, like the energy conservation and things like that, but fundamentally it doesn't follow from anywhere. All right, so we can say that in physical space this state vector would look like a wave, right? So this is our wave function, and for free particles it really looks just like a wave. I don't know what's there to talk about also, but you can clearly see already that there is this paradox where you can describe the localized particle with like an infinite wave, and I mean, well, that's obviously a paradox. Like what the hell is going on? And it is indeed a paradox, and we'll talk about it a little bit more later. So there have been some interesting experiments to kind of demonstrate these properties of quantum systems. Like one of the most famous is probably this double slit experiment, and we'll talk about it right now, in fact. So this is like a there's a meme about, you know, JPEGness of an image that involves this character. So it's, yeah, I thought it would be, it's a jackal.
Jackal. Okay.
Yeah, so the JPEGness of an image is measured in jackals, basically.
Okay.
But anyway, yeah, but we'll utilize him actually later. So what we have here is these are like three different situations, these three blocks. So we have some sort of source of particles, this guy. Then we have like a screen with two slits. And then we have a detector of particles. And this thing is what kind of statistics the detector is observing. So, you know, here it catches many particles, then here it's a bit less, here it's even more or less, and so on. So this is the statistics. It's not something, you know, spatial. So we have these two slits, and if one of the slits is open, then particles naturally mostly, you know, hit the detector like right against it. But as we move farther away from this line, there is less and less particles being detected. And it's kind of understandable, right? I mean, classical particles would move like that also. And then if you have the other slit opened, but the first, you close the first one, you have the same thing, but, you know, moved towards the second slit. But the thing is that if you have both slits open, you observe this interference pattern, right? So it almost seems like these particles, they kind of stifle themselves in some areas, but they kind of how do you call it? Like enhance themselves in other areas, and you get these series of peaks and troughs. So yeah, this is pretty much what I already said. But the interesting thing is that the same thing is observed even if you emit the particles one by one. So you would still see this type of statistics in the end. So it almost looks like the particle interferes with itself, which is again an indication that it's not really a particle, but it's rather a wave. And it also seems like this particle kind of moves through both of the slits simultaneously, which is sort of mind-blowing. And even more so, there is like a very cool enhancement of this experiment where you wait for some time, like you pass, like say this distance is very big, all right? So you kind of send the particle through. It kind of already somewhere here, but if you at that moment change the configuration of slits, the particle would kind of know about that, and you would still get, you know, the according pattern. It's the so-called delayed choice experiment proposed by Wheeler, and it has been done, and this is indeed the case. So it's kind of, and it's actually, I'm kind of digressing here, but I think it's important to make this comment that for quantum mechanics, time is really just a free parameter. So the evolution of quantum states is completely determined in the sense that you can go forward in time or you can go backwards in time. It doesn't matter. Like, you know, each state is completely determines the next states in the future, and it's completely determined by all the previous states. So in a way, you can say that the particle was actually moving backwards in time, you know, and kind of encountered this change of slit configuration and so on. But it's a kind of a hardcore comment. I wouldn't don't think about it too much, basically. Yeah. So and another interesting thing about this experiment is that if we have both slits open, but we also have some observer kind of who wants to know like what the hell is going on. He tries to detect where exactly this particle is. Like, does it really pass through both slits simultaneously? So if he detects the particle somehow, like if it emits a photon that he catches, then he would know that the particle, say, passed through the first slit. And even if the second slit is open, you wouldn't see interference pattern anymore. So, and the same can be said about the second slit. So the interference pattern only appears if you don't produce any observation, if you don't interact with this particle. So it seems like, almost like the introduction of any additional objects into the system, such as this observer that interacts with the particle, it kind of destroys this third superposition state. I would actually say that, like using my previous language of these state vectors, you can say that this state vector would correspond to particle that passed through this slit, and this state vector would correspond to this slit. But you can also have this superposition where it passed through both of them, right? So this third quantum state is only possible, again, if you don't introduce any interference in the sense that, you don't mess with your system, basically. Yeah, this is pretty much what I already said. And there are other interesting properties of quantum systems. Like one of the things was this famous uncertainty principle of Werner Heisenberg. So it states that there exists pairs of physical quantities which you cannot simultaneously measure with infinite precision. Like your precision would be limited by this factor, by this Planck's constant, essentially. So the examples of such pairs would be coordinate and momentum, or energy and time. So the more precision you get with, say, measuring the momentum, the worse the situation is going to be with coordinate, and vice versa, or with the energy and time. It's the same concept. And I should note here that this is also basically a postulate. It doesn't follow like immediately from the first principles. It's important to know that, but again, it's supported by observations, but we still have no idea where it comes from. Well, we have some idea with these modern alternative theories, but that's not the topic that I'm going to discuss here. So in quantum mechanics proper, it's just introduced by hand. So so one of the consequences, well, I kind of mentioned that already, but the other consequence of that would be that even the energy of a system might actually change, kind of violating, the conservation of energy, where you can have this delta E, this change in energy of that size, where this delta T is the according time. So if delta T is very small, like, I don't know, 10 to the minus 20, then the energy of your system might actually change quite a lot. So this is what allows so-called virtual particles to exist. So if we say that they kind of appear and almost immediately disappear, so this delta T is very small, then they can have like a pretty significant energy. So yeah, this is what we get. And kind of to conclude this section about the basic description of quantum mechanics, I wish to draw this comparison between classical mechanics and quantum mechanics. So in classical mechanics, we've had the position of a particle, like, coordinate. We've had the velocity of a particle, so it's just, the derivative of coordinate, like it shows us how quickly the coordinate is changing. Then we can have acceleration, which shows us how quickly velocity is changing. Then we can have force, like, the Newtonian dynamics in it. The force just really shows the link between acceleration and mass. And we have the conservation of energy, and we have like precise predictions for the world. But in quantum mechanics, like the whole description is completely different. Like, first of all, we're not even dealing with space, as I've said. We're dealing with state vectors. And that, again, show us in which quantum state the system is in. And the kind of spatial representation of state vector is only, a particular case. Then we have these weird superpositions, which are absent in classical mechanics. Then an interesting conclusion from Heisenberg's uncertainty is that position and velocity cannot be determined simultaneously, which and from that it actually follows that quantum particles cannot have trajectories, because what trajectory is, it's a statement that at this moment in time, the particle was here, at the next moment it was there, but we cannot do that if even the position itself is not determined. So, you know, all these pictures where you have atom and electrons like literally orbiting it, they are very wrong, because, well, there's no such thing as the trajectory of an electron in quantum mechanics. Then acceleration cannot be determined, obviously, because we don't have like the very concept of velocity. Force cannot be determined, again, because we no longer have acceleration. Energy is not determined, or it might change, you know, as I've shown you. It's a consequence of Heisenberg's uncertainty. Like the states for which the energy is determined are, it's a very special case, and they are called stationary states, but they're only like a fraction, you know, of all the possible quantum states. And we have probabilistic predictions, essentially. So we're dealing with statistics usually, again, because of all these uncertainties and things like that. So I would actually like to make like a philosophical comment here, because, well, you know, some people actually say, well, or everything is energy or something to that effect, you know. Well, at least according to quantum mechanics, this is not the case, because you cannot even determine energy, you know. So, well, there you go. but we might talk about that a little bit later, like when I finish. Right, so let's talk about the paradoxes and interpretations. So here I'm giving you a short list of what I'm going to be talking about later, like in the next few slides. So some of the paradoxes might include this question that I've already asked, like, what are we dealing with here? Are those waves, like infinitely big waves, or are these particles, you know, localized solid balls? We have obviously Schrodinger's cat paradox, the very famous one, which is all about these quantum superpositions. Then we have the problem of so-called wave function collapse, which deals with the question of how exactly and where exactly is, you know, the border line between the quantum world and the classical world. But we'll talk about that later. I'll try to illustrate it on Schrodinger's cat paradox. And then we have Einstein-Podolsky-Rosen paradox, which is about quantum teleportation. So I'll briefly talk about all these points in the later slides. And afterwards, in the next section, we'll talk about interpretations. So we'll describe some of the most popular interpretations, such as Copenhagen interpretation, many worlds interpretation, informational interpretation, and decoherence, where I need to make a caveat that decoherence isn't usually considered to be a separate interpretation, but I think it's valid to be considered that way. Okay, so this question that I've already asked again, are we dealing with waves here or particles after all? So, like, there are, you know, indications that might support both of these points simultaneously. Like, we're definitely seeing, like, with this quantum interference in double slit experiments, that it seems like a wave function is the proper way of describing it. But at the same time, we see that the interactions themselves are discrete. They're like point-like and local, so which would be an indication that it should be particles and not waves. So the question still remains, like, what are these? Are they particles or waves? Like, what are we dealing with here? What are quantum objects fundamentally? And I'm afraid that this question cannot be answered at the moment. Like, nobody really knows. People like Bohr proposed this really stupid way of dealing with it, I would say, which is called principle of complementarity. It's basically, you know, like trying to solve a problem by just postulating it, you know. So he just says, well, okay, relax, guys, like quantum objects behave as particles or waves depending on circumstances, you know. So it's not a bug, it's a feature, you know. So it's that way of reasoning, essentially. But there is still no, like, analogy, no model for what they are, like, in reality, you know. And we have this so-called wave-particle duality, which is, again, stems from this principle of complementarity. Now, Feynman kind of made a pun. He said, well, relax, guys, these are wavicles, you know, like wave plus particle. But unfortunately, nothing better has been brought up since then. You know, this pun is the best that we get so far. So yeah, it's a big problem. And by the way, I would say that this is one of the illustrations of, again, kind of going onto philosophical rails. This is a good illustration of constructivism in science. Like you have this one construct of a wave and one construct of particle, both of which are valid simultaneously, but they are mutually exclusive, you know? So how can you deal with that without constructivism? That's a good question. But anyway, okay.
Don't worry
so
about
let's talk. Huh?
Don't worry about it.
Yeah. Well, that's the best that theoretical physicists have come up with, unfortunately. So Schrödinger's cat is a very famous paradox. So it's a thought experiment that actually demonstrates the absurdity of the existence of quantum superpositions. So, and it boils down to the, you know, this situation where a state of a classical system, which is a cat in this case, depends somehow on the state of a quantum system. Like you say you have some, you know, vial with poison that would, you know, break and kill the cat if some nucleus would decay. And since the decay of the nucleus is inherently a quantum process, so the nucleus can be both in the state of decayed nucleus and non-decayed nucleus. And therefore, since the state of the cat depends on it, the cat also should be in this superposition state, you know, of dead cat and alive cat. So, this kind of demonstrates, well, but basically it's you know, like all the problems of quantum mechanics can be demonstrated on this like thought experiment. So again, you have some, let's say, decaying nucleus, and you have the poison that it releases. So since the nucleus might be decayed and non-decayed, and both of them simultaneously, therefore the cat should also be dead, alive, and simultaneously dead and alive. And I should stress that moment that the paradox is not just simple ignorance of ours, you know, that we just simply don't know whether a cat is dead or alive. But the paradox is about that it's actually simultaneously dead and alive. This is the core of the problem. But you see, when we perform observation, like when we open this box, then somehow this third state vanishes, right? We either see a dead cat or a live cat. So, and this disappearance of this third option, kind of a irreversible change of state vector, it's exactly what is called this wave function collapse that I mentioned previously. And by the way, there have been other attempts at formulating similar paradoxes, like Einstein, for example, proposed pretty much the same setup, but instead of a cat, there was like a gunpowder there. So you would have like a gunpowder that kind of exploded and not exploded simultaneously, which is even more paradoxical, you know, because you obviously can hear if it explodes. So there you go. But fundamentally, it's the same paradox. So yeah, so we have this strange phenomenon where this quantum superposition somehow is not observed. So yeah, this is something that I already mentioned. But we can go further, actually. So Eugene Wigner, he proposed an enhancement of this Schrödinger's cat paradox, which is called, well, Wigner's paradox, or paradox of friends. So let's say that this jackal has many friends who still, like Jackal has observed the state of the cat, all right? So he already got one of these two results. But his friends still don't know what kind of measurement has been done. They don't know what the result was here. So the question is this system still in superposition for them, you know? And when exactly does this superposition vanishes? Like it's when everyone in the universe would know the result of this experiment or something, you know? So it's a very interesting question.
So it only disappears for the observer?
Well, technically, yeah. You know, in purely quantum mechanical terms, what happens here is that the state of the observer becomes entangled with the state of this system. So, yeah, and you know, like, and it should still have this superposition also, for at least the external, like the other guys.
Right. Right.
Yeah. So, and it's a very hard question. It's a very fundamental problem. Like when does it happen?
Yeah.
You know.
Depends on how pixelated you are. Right?
Yeah. Well, this is exactly what I said about the measurement of JPEGness.
Right.
All right. So, but
so Eugene,
I mean,
is that where like the idea of time travel comes into the quantum kind of picture, right?
Not exactly sure.
Time is kind of a variable, right?
Well, yeah, time is a variable. Yeah. So, what are you saying?
Well, sometimes you get some of the ideas that time travel is actually possible in quantum concepts, right?
Well, from the standpoint of quantum mechanics, I would actually say that it's rather not possible than possible, because again, like time is just like a free parameter. So you can kind of go forwards or backwards, and it doesn't change anything. I mean, in terms of the description of quantum values. So, in a way, well, I don't know. It's actually a good question. Yeah, I haven't thought about it much, but I mean, like again, this sort of thing, you know, this irreversible change in quantum state, which is called the wave function collapse. It definitely breaks this what is called unitary quantum evolution. You know, so it's something else. You know, so in this sense, quantum mechanics actually does depend on time. You know, these measurements, they definitely introduce something else to the quantum system, but again, it's a problem. It's not an answered question at the moment. So, like, many views are possible. Yeah, I don't think I answered your question, but
no, I think I get it. Like I was just thinking, like you got three different states, right? Dead, alive, and or both at the same time, right?
Yeah.
So it's kind of introducing that time would not necessarily be considerable as a constant in that sense, where it's a breaking of time symmetry, I guess, might be a better way to describe.
Yeah, exactly. Right. So this measurement, when it eliminates the third option, it's definitely breaking the time symmetry. Yeah, and again, it has to be dealt with separately. Like, people don't know how to deal with it actually, because, well, again, this is one of the most fundamental problems. Like, where does the quantum stops and classical begins? You know. But we'll talk about that in these interpretations sections, because there are some approaches here. But so far, I want to briefly talk about this so-called Einstein-Podolsky-Rosen paradox, or EPR. So what we're dealing with here, and I'm actually kind of also not very honest, in the sense that these guys were actually talking about a little bit different thing, but it's also very related. So in this sense, it's valid what I'm going to say. So in a nutshell, what we're dealing with here is that if we have the entangled states of two particles, all right, but if we separate these particles on a large distance, let's say, their states would still be, in quantum mechanical terms, correlated, which would mean that if you make a measurement of one particle, or, you know, interact with it in some way, then the change of its state because of that interaction would immediately change the state of the other particle, regardless of how far it was, you know. So this is the thing that kind of bothered Einstein a lot. I mean, you know this concept of spooky action at a distance and so on. So, but usually it is called quantum teleportation, this immediate change of one of the particles' state when you interact with the other particle. But again, the point of entry, so to speak, here would be the fact that these particles were in entangled state before you did that. So you can probably consider something to that effect. So if we have this system in an entangled state with two quantum objects, and there is this, again, their states are correlated. If you separate them somehow, like for example, it might be, again, a decaying nucleus, right? So these are the daughter nuclei that appeared when it decayed, and they just kind of fly away in different directions. But they're still correlated, they're still entangled, right? They're quantum states. So what happens is if you try to interact with one of these particles, say you're trying to measure it, and you get this state, then, you know, this quantum teleportation occurs where instantly the state of the other particle also changes. So this is, in a nutshell, what is called the quantum teleportation. But what we need to, I actually thought there was another slide here. Okay, so what we need to know about it is that, what I need to stress, I guess, would be that no energy has been transferred during this process, no matter has been transferred, and no information has been transferred. So what gets teleported, so to speak, is, again, this abstract quantum state, all right? But so it does not mean that you can have faster than light you know, communication, exactly because when you measure something in your laboratory, the particle in the other laboratory, like you would know what kind of state it has, but the guys in the other laboratory who has not done this measurement yet, they still don't know it, right? So you cannot transfer any information to them that way without invoking, you know, regular means of communication, such as, well, I don't know, radio, internet, or whatever. So any kind of quantum communication would always require additional classical channel. So it's not only, you cannot communicate through quantum channel. The only thing it does is, well, okay, we'll talk about this in this cryptography, actually right now. I mean, the possibility of application of that to encrypting your signals, basically. So the thing is that if some third party tries to monitor these quantum particles that you exchange with your, I don't know, friend, then by measuring the states of these particles, you would know that some, you know, external influence is present. So some, you know, eavesdropping is taking place. So this is the fundamental thing behind quantum cryptography, is that, well, again, any sort of messing with your quantum channel would be easily noticeable. So, and it's a very frequent example of that, where in all these papers on quantum cryptography, you would always have Alice and Bob. I think people actually just got bored, you know, just naming these guys A and B. They kind of named them Alice and Bob, who exchange these entangled particles and measure them, but they also have some classical channel of communication to kind of let the other party know what kind of result they have. So if they stop seeing these correlations, it means that some third party actually tries to intercept these signals, right? And it's usually called Eve. I think it's like a shorthand for eavesdropper or something, you know. But it's a very standard terminology in quantum cryptography. Like we have Alice and Bob and we have Eve. So they would notice that something is wrong with this entanglement if somebody else tries to eavesdrop. But this woman, she actually allows me to perform some other weird quantum effects. But that's which also makes Bob pretty concerned, let's say. But anyway, so yeah, that's pretty much that comment I made previously, that quantum teleportation, it happens instantly, but it does not transfer any energy, matter, or information. So you know, relativity principle actually does not suffer from it. The only thing, again, which gets transferred during it is the quantum state, this abstract thing. Yeah, I think this is all I wanted to say about it. So let's now talk about these interpretations. So it's like a large, it's a big thing, you know. You can look it up on Wikipedia. There's a huge article on interpretations of quantum mechanics. So this is like a running theme that was around for quite a while, actually for like 100 years already, or about so. And there are many different interpretations, or about 10 or 20, I would say. So you see, the thing is that people cannot even agree on the classification of those. So that's how bad it is at the moment. So, but the most popular, I would say, at the moment are these four: Copenhagen, many worlds, informational, and decoherence. So we'll talk about them for the sake of brevity. So this has been some sort of poll at some conference where, you know, the question was asked, like, what is your favorite interpretation? And you can clearly see that these three first that I mentioned, Copenhagen, many worlds, and information, are the most popular. But again, as I've said, the coherence...
Pretty recursive. Probabilistic.
Oh, yeah. Yeah, it's kind of an interesting aspect of it. As I've said, decoherence isn't even usually perceived as a separate interpretation, but I think it's valid as a separate interpretation. So I use it in that way. And there has been another question at the same conference, like, well, what the hell do we do with this problem with measurements, you know, opening the cat box and so on. So about 15% think that it might be solved by decoherence, which is not bad, I would say.
Pseudo problem, I love it.
Yeah. I mean, yeah. And this point is also very interesting. Like, none of you, what do you mean by that? Okay, so let's talk about the like by far the most popular one. It's the Copenhagen interpretation, which is obviously proposed by Bohr and also promoted by Heisenberg. So the thing is that it's very simple, it's very straightforward, but it's very problematic from, you know, from the standpoint of the picture of the world. So in this interpretation, we just postulate, you know, like artificially state that there are two different types of objects, quantum and classical, and they behave differently, right? And during the interaction of a quantum object with a classical one, the quantum object kind of loses its quantumness, so to speak. So all these superposition states, entanglement, all of that disappears. So there's in this irreversible collapse of the state vector. So we just announce this being a feature rather than a bug. You know, this is kind of a way of doing things with regards to Niels Bohr, as far as I understood. He kind of liked that approach. Basically, you know, calling any problem actually just a property, you know, of the system, and so on. So the advantages here, and why is it so popular, is that, well, again, because it's very simple, and because it's instrumental in the sense that you can calculate stuff with it without, you know, thinking too much, and that's what people do, most of the, you know, people in quantum mechanics realm. But the disadvantages are also pretty clear. Like we don't know what is the reason for the fundamental difference between quantum and classical objects. We just postulate that there is a difference, but what it exactly is, we have no idea, and it is unclear where is this boundary. Like at which moment a quantum object becomes a classical one. And again, one could ask, well, like exactly when does an object become classical rather than quantum, or vice versa? And it's also not clear from this interpretation. And it is unclear what role is played by the observer and consciousness. We'll talk about that in the very latest slides about consciousness and so on. But here it is like a hanging question. It's not addressed in any way. I mean, in Copenhagen interpretation. All right. So another very popular one. It's actually, I think, it's gaining popularity more and more in recent years. I kind of tend to notice something like that. So in this interpretation, what we're dealing with is like the branching of the universe itself. So let's say, again, with Schrodinger's cat, like in one universe, it remained alive. So this corresponds to one quantum state. And in the other universe, it died, right? And when you perform some measurement, you just kind of instantly transfer to one of these universes, one of these worlds. So yeah, well, there you go. This is pretty much in a nutshell this interpretation. And there's an interesting offshoot of that is this paradox of quantum suicide, where basically if you sit in this box instead of a cat, there would always exist a branch, some branch in this multiverse, so to speak, where the nucleus did not decay, and you kind of would be alive forever in this sense, like you would never die. But this is like there has been so many of that type of paradoxes proposed over the years. I'm really only mentioning the most basic ones. But I mean, you can just appreciate how many free time these guys have. Okay, so the advantages of this interpretation is that it doesn't contradict really all the mathematical formulation, and in a way it explains this process of wave function collapse. It just you're getting kicked into one of these universes, so you no longer have superpositions and so on. But the problem is, I believe, is that, again, it's not clear like what is the difference between classical and quantum objects here. Like does the universe branch for any type of object, or like only very small objects, or what the hell, and so on. It obviously contradicts Occam's razor, because, well, basically to explain the state of one electron, let's say, you need to invoke a whole other universe, which doesn't seem very economical to me, at least. And since these parallel universes do not interact anymore, right? So since this branching has occurred and you were just following one of the branches, so why do we even need all these parallel universes? Like, we would never know if there is another universe because we're already branched away from it. So this is a pretty strong issue with that type of approach. And again, it is not clear what is the role of consciousness here. And I'll mention that again a bit later. There's at least one guy who has a pretty interesting theory about it. Okay, so another very popular interpretation is this informational one. And I would say that you can kind of arbitrarily divide it into two branches. I would say there is a conservative branch and there is a radical one. So conservative one just says, well, okay, quantum mechanics describes not the world itself, but only our knowledge about it, right? So you can frequently see statements like this one, that the state vector is like only our notebook, right? It only depicts what we know about the world, but not the world itself. So in a way, it's, and because of that, it's related to all these processes like observation and so on. So it's not the world itself that is changing, but only our knowledge about it. And there's a more radical approach, which says that information is actually a more fundamental concept than matter and energy and so on. So kind of the quantum information, the quantum objects, they kind of precede classical objects. Like Wheeler again had this idea of it from bit, like the emergence of being from information, essentially. I would say that such a division can be made. So the advantages of such an approach is, again, well, it does not contradict the basic formalism, so you can use it and survive, so to speak. But at the same time, in my opinion, it leaves out fundamental questions, ontological questions, philosophical questions, like what is reality, and so on. I'm not very happy myself with that kind of approach, but I don't know, maybe you would like it more. All right, so let's talk about quantum computers a little bit. So basically what we're dealing with here is that we have classical bits that can have only one of two states, right? But in quantum bits, they're also called qubits, you can have superposition of these states, right? As I've said, you can just take the sum of these states. And in fact, they might be of different length, you know? So it is frequent to depict the state of the qubit in this spherical kind of shape. It's called the Bloch sphere. Bloch is a last name. So you can have any type of vector here. And they also can have phase. So you can rotate it, but that's more, you know, it's an like applied approach, because people who deal with quantum information, they need to have some vehicle to do that, and they use this sphere as their main instrument. All right, so and theoretically, different qubits also can be in a entangled state, and what's good about it is that you can perform like parallel computation of many different outcomes, and it's very important, let's say, in several like difficult problems in mathematics, such as factorization of numbers, for example. You know, the how do you call it, to divide a number into factors. This is one of the most important mathematical problems, I mean, in terms of computation. And supposedly quantum computers can do that much better than regular computers, and so on. So, but there is a problem with realization, the practical realization of quantum computers, and it stems from the fact that the environment, you know, everything that surrounds these quantum bits might interact with them, like, you know, through literally just heat or something to that effect. So, and that would destroy this quantumness. Again, it's kind of opening the cat's box, so to speak, and which it would change the state of quantum bit into a classical bit. You know, it would ruin your superpositions and entanglement and so on. And this process is called decoherence. This process of disappearance of quantum properties due to interaction with the environment. But and by the way, like practical realization of qubits, we might use separate particles, we might use spins of particles, even in a lattice, like, you know, solid state, or we can use molecules, or we can use photons, and so on. So there are many different avenues here. But anyway, so some people looked at that and said, like, wait a minute, maybe we can use this very same process of decoherence to explain like this wave function collapse in the first place. Like so, and here goes this other interpretation that I actually think it's the most profound one, like the most logical one. So it states that the state vector collapse, this, you know, irreversible transition when we get rid of quantum superpositions and so on, it might be explained as a consequence of the interaction of the quantum system with the environment. And so that way, the information about these purely quantum states, these superpositions, they would be, this information would be kind of smeared over the environment. Well, it's kind of might be quite difficult to understand, but I'll try to illustrate it a bit later. And so if the environment is large enough, it would be almost impossible for you to reclaim this information, to kind of gather it in one spot again. But although theoretically, I should note, it would be still possible. Like, so there is no, well, okay, I'll mention that later. But anyway, there are so-called no cloning and no hiding theorems in quantum information theory that clearly state that quantum information cannot be destroyed, all right? If you interact with a quantum system, it's just that you yourself now contain some of that information that previously was in that quantum system, but it does not disappear. It's just now it's kind of smeared over this much larger system, which is you in that case. So, and that makes it almost impossible to return back, so to speak. So you can imagine that as like, again, very abstractly speaking. So let's say we have this environment, something, you know, some classical object, and we have a quantum object inside of it, which is like a blob with paint, let's say, right? And so if you kind of switch on the interaction, the environment kind of punctures this blob, and the paint kind of gets smeared over the environment. And since the environment is very big, like you cannot collect it again, you know. And well, it's obviously not a strict approach. I'm just kind of trying to illustrate the main idea of this decoherent approach. And it has been shown that the characteristic time of decoherence is proportional to Planck's constant squared divided by mass of the system. So first of all, it's a very little time. I mean, Planck's constant is very small. And the more mass you have in the environment, the quicker it happens. So in that way, you can explain why large objects, the classical objects, don't have, or at least don't demonstrate quantum properties. And like some real clear advantages are here, I think. Like all the equations of quantum mechanics are valid, so it does not contradict anything, and which is most importantly, even more important, I would say, is that the fact that there is no clear boundary between quantum and classical world. You know, the classical laws are only like the approximation of quantum laws, which are valid for these large systems where superpositions quickly decay because of that type of process. All right, and it kind of eliminates the very problem of wave function collapse, because, well, it doesn't really collapse. It's just not observed anymore in that particular object that we're talking about, but it's still somewhere there. Like this quantum state does not vanish, all right? And I believe it's an adequate answer to the role of the observer. Like, the observer is not needed, strictly speaking, like, and the consciousness is not required, like, because this process might occur like with any types of objects, right? And even more so, like, returning to this paradox of Schrödinger's cat, I think you could say that the decoherence of the state of the cat would occur like long before it would reach the cat itself. Like, already, you know, this vial with poison, it's already a huge classical object. So the decoherence would happen already there. And even more so, like if you have heat waves there, you know, the infrared photons, they would interact with this nucleus and when with the vial with poison and so on. So decoherence would appear very early, and like the quantumness of this nucleus would be sort of not observed already at that point. So yeah, but I don't really know what to say about the disadvantages. Like, I think, like, maybe it might piss some people off because, you know, it removes some magic, you know, but that's probably the only disadvantage that you might bring up. All right, so I'm pretty much moving closer to the end. So I just want to mention some of the points that are really important, but I've completely omitted them. Because, well, again, I wanted to cover only the basics. So one of the important things is the formalism of density matrix, where you, instead of dealing with state vectors, you're dealing with this, again, so-called density matrix. And it has nothing to do with like regular density, you know, mass divided by volume. It's a completely different object. And it's a more general, but at the same time more complex formalism. So there are some quantum states which cannot even be described by state vectors. So only for simplicity, I was using that thing. But in the most general sense, you should use density matrix. But like fundamentally, like you can have all the characteristic quantum effects even with state vectors. So it's not a problem in that regard. Then I didn't say anything about the quantization of energy levels, right? Which is one of the most prominent properties of quantum mechanics. I didn't talk about quantum numbers and how they arise, like the numbers like spin and so on. Then there's an important thing called Pauli's exclusion principle, where if you have particles with spin 1/2 of Planck's constant, they cannot be in the same state. They should differ in some quantum numbers, and so on. It's a very important principle, and again, it doesn't follow from anywhere, but it's super important for atomic physics, for nuclear physics, and so on. Then I haven't said anything about multi-particle systems. Well, I kind of briefly mentioned these entangled states, which you can have if you have more than one particle. But there is a very profound, very well-developed approach of so-called secondary quantization, which is what quantum fields are based on. So I did not talk about that at all, about the statistics and so on. But it's an important subject. Then there's an interesting thing called quantum Zeno paradox. Now, Zeno is a Greek philosopher. You know, he has this paradox of an arrow, where he basically kind of proves the non-existence of motion, basically. He says that, you know, you look at an arrow at that moment in time, and it doesn't move anywhere. You know, I mean, if you fix this moment in time, then you look at it in the next moment in time, and it's also not moving anywhere. Therefore, you know, the motion does not exist. It's a pretty interesting turn of thought. But there's like a quantum version of it where it can be mathematically proven through, again, all these formalisms of quantum mechanics, that frequent observation of a quantum system actually reduces the probability of the change of quantum state. And you could probably observe that effect if you receive your salary on a bank card, and, you know, the more frequent you check your balance, the less probability is that you actually have wage there. But maybe there's some quantumness here. But anyway, so there is also so-called tunneling effect, which kind of follows from the fact that the spatial representation of state vector is a wave function, right? So, and the effect is such that essentially there are no impenetrable barriers, and quantum objects might kind of leak in anywhere. Why is it called tunneling effect? It's like, you know, the particle kind of moves through some tunnel, even though, you know,
like overcoming an energy state kind of thing.
Huh?
Like overcoming an energy state that wouldn't be expected.
Yeah, exactly. So the particle might move in some. It might tunnel through these, you know, potential energy barriers, even though it might not have enough energy to do that. But it still can do that. It's just, you know, the probability is pretty low, and so on. But actually, again, like, for example, some of my colleagues have shown that this effect might be severely enhanced if you introduce some special type of perturbation to the potential energy. But that's a different subject. But it's a known thing, and I mean, in solid state physics, and again in this semiconductor technology, it's actually utilized there. So it's not something, I don't know, it's not something purely hypothetical. It's a real thing.
Right.
And then there's an interesting thing called Casimir effect, where you can essentially get like free energy from virtual particles. So the effect is such that if you have two like plates, let's say metallic plates, and they are fairly close to each other, what that would mean is that there is more, like in the space between these plates, only certain types of standing waves are possible. You know, there's a very finite amount of standing waves possible inside, I mean, in between those plates. But outside of them, all the possible wavelengths are possible, you know? So you have this, like, literally pressure from these virtual particles, because there's kind of more of them outside the plates than inside of them, I mean, in between them. So you get this pressure, and theoretically, I mean, you can get free energy from that. And it's actually, I think it actually has been experimentally proven. The only problem is that it's a very small effect, but it's still there. Then I haven't said anything about Feynman's approach, where it's a very interesting approach to, and it's a very practical because it allows you to calculate stuff, where basically what he does is he proposed to calculate the probability that a particle would be at some point. You should take a sum of all the possible trajectories it could have traveled, you know. And if you take this sum, of course, it's going to be an infinite sum. It's going to be an integral. But in some cases, you can calculate that, and you get the correct result in the end. And it's a very interesting. It kind of relates to this point that I made about double slit experiment. You know, when it seems that the particle moves through both slits simultaneously. So it's just a generalization of this point, this Feynman's approach. Then there are interesting theories such as Bohm's mechanics, aka pilot wave theory, the so-called theories with hidden parameters. They are, well, in particular, Bohm's mechanics, it is, one interesting thing about it is that the conclusions are absolutely the same, like mathematical result is indistinguishable from regular quantum mechanics, but it utilizes a completely different approach. So it's a thing to look into if you're interested in these interpretations of quantum mechanics and so on. But I mean, I haven't studied it much, but I definitely know that it's a thing, you know. It's probably worth looking at. All right, so again, let's talk about the more vague philosophical stuff. So I've already mentioned that in these many worlds interpretation, at least, some of the consciousness might actually be introduced as an important factor. And for example, there's a Russian scientist, Mensky, who actually thinks that it's the consciousness which kind of regulates the process of this branching, you know, of the multiverse. So what he says is that somehow with your consciousness, your consciousness determines which branch are you going to travel in, you know, after you make the measurement. So, well, there you go. I mean, I don't agree with that, but, well, there are many different opinions. And there are, you know, people like Deepak Chopra or Wigner, the guy I already mentioned, and Pauli, who kind of all, you know, focus on this possible importance of consciousness, and again, in relation to quantum mechanics. But I'm kind of, sometimes I get pissed off by all that, because to me, it seems very quasi-religious. Where, you know, like quantum is basically a shorthand for magical. So there's this quantum mysticism is definitely a thing in modern culture, and I don't like it.
Yeah.
I mean, some people might like it, but sure. Yeah, and well, okay, I'll make that comment later. But so this book I actually liked quite a lot. So it's, as you can see, it's literally called Quantum Magic, and I don't think it's available in English. I've read it in Russian, but like he also introduces, there are many doubtful hypotheses, I would say, especially at the, you know, later chapters. But one interesting thing is that he actually gives a very good and coherent statement of the basics of quantum mechanics. So I definitely learned a lot from that book, even though I don't agree with the conclusions. But anyway, but with regards to English, I don't even really know what kind of literature I could recommend. because, well, basically most of the material I've read was in Russian, but so I don't know what to advise you to read if you want to learn more. Okay, so another philosophical note. Again, even if we're dealing with this decoherence interpretation, I think I mentioned that fundamentally, this quantumness does not disappear, right? So even if you make a measurement of a quantum system and you kind of get one of the two results, it doesn't, like, theoretically, from the standpoint of quantum mechanics itself, this third state and all the correlations, they're still there. I mean, in the overall system, it's just that you are also included in that system already, so you are part of it now. And you also contain some portion of this quantum information, speaking very vaguely and abstractly. So any particles that ever interacted, which would probably mean any particles in the universe at all, because, well, they've all should have interacted at that point or another, directly or indirectly, it doesn't really matter also. So the states of all the particles in the universe should be correlated. They should all be entangled. And that's a pretty strong conclusion, pretty strong statement, but it follows from quantum mechanics. Like, the thing is that, again, these correlations might be not noticeable in the sense that, again, the coherence kind of suppress their expression, but fundamentally they should be there. That's what I'm saying. And this famous quote by John Donne that no man is an island entire of itself, and so on. So yeah, all this stuff should be connected according to quantum mechanics. Of course, it might be wrong, but that's a different question. So, all right, so I guess this is like the most general conclusions from this presentation. So I would say that we might divide conditionally quantum mechanics into these two parts, as I've shown to you in the very beginning. This technical part where we have, these equations, abstract objects, all this formalism of Hilbert space and so on. And we also have this humanities part, which deals with the picture of the world and interpretations and trying to understand what we're dealing with in the first place. So my claim here would be that technical part works decently well, and it has produced all these practical applications and so on and so forth. But this humanities part is seriously lagging, like at least 100 years. And it does not provide any kind of unified, simple, and coherent picture of the world. I mean, as you could see, people cannot even agree on how many different interpretations are there, not let alone like which is the correct one, etc. So this quantum world is significantly different with respect to the classical one, and the question of how are they related is not answered at the moment. But there are various attempts at answering it, and they are called interpretations of quantum mechanics. And again, it's a kind of a running topic here. There are very many of them. Now, I did not include this point here, but I would also like to mention that recently I've become aware of many like alternative approaches to particle physics and so on. And I can say that perhaps actually quantum mechanics might be just a consequence of some sort of, well, to speak vaguely, electromagnetism, So all these phenomena might be explained through some more fundamental nonlinear electromagnetic theory. But that way or another, as I've said previously, you would have to keep like these. Well, you have to basically get the same equations because the equations seem to be correct. That's the point I'm making. But anyway, yeah, like I've probably ranted enough for today.
That's great.
So thank you,
Eugene. Awesome. Just just a lot of detail, particularly for an introduction for everything. So I'd like to personally open. Thank you for this is actually kind of the the reintroduction of what we've been up to with Jim and I on this EU meetup. So thanks for kicking it off here, and I'd like to open it up for questions for Eugene.
Yeah, well, you're welcome. Yeah, so let's discuss it if you have any points.
I was just wondering what your thoughts were on, do you think it's, from a quantum perspective, as far as, can the field perturbations determine particle states? Like, so the field is causal, where you have coherence and incoherence, where waveforms interfere. So constructive and destructive interference, can that determine the state of a particle, or for it to manifest as matter at a point in space?
Well, you're kind of when you're talking about fields, this is already a much more complex object than a quantum particle, because a field is essentially a bunch of quantum particles. So it's kind of, a circular reasoning in a way to say that the field determines quantum particle, because, well, the field is a bunch of quantum particles, So not sure if that answers your question, but yeah, by the way, yeah, I would say that quantum fields are currently considered to be like the most fundamental objects in nature. And then like these particles or waves or whatever is just a excited state of a quantum field. That's what it is. So, yeah.
Well, that basically what you just said at the end is basically what I was thinking. Yeah.
Yeah, and
it becomes deterministic, right? Where the interference, destructive and constructive, is deterministic, where the particle actually is at any point in time. Yeah, as a quantum field is a quantum particle. Yeah. Makes sense. Yeah.
Well, you would still have all these things like Heisenberg's uncertainty. So it's not very like 100% deterministic. Like the quantum state itself is deterministic. Like you can calculate it, but the problem is that a measurement, like, well, it's actually like, yeah, there's one interesting other interpretation that I haven't talked about, where it's basically, one could say that it's a statistical interpretation, where you say that state vectors actually do not describe individual particles, but they describe like ensembles, infinite ensembles of the same type of particles, So in that way, you can explain the statistical character of quantum measurements, that you can only get the probability of say getting certain physical quantity rather than the exact result. But that's a whole other approach to the whole problem.
Yeah, one of the things I remember is from just the semiconductor physics and the movement of like carriers, etc., under electric fields. But is there a place to kind of, like, from the description that you gave, what would be the vector to kind of incorporate like the perspective of those, they have the movement of holes and that kind of stuff. Do you have a feel for like where from the presentation we would point into that area?
I don't exactly understand what you mean.
Yeah, well, like charge carry. I know it's usually a quantum mechanical concept, at least, like charge carriers in a semiconductor, when there's a certain p doping and an n doping and that kind of thing.
Yeah. So
the in perhaps my oversimplification of the thing, it seems that type of reasoning and modeling could be done without a quantum mechanical model.
Well, in some cases it might, but in some cases it might not. Like if you look at even how people in solid state physics work, they start from quantum mechanics, like to determine the temperatures. They have to consider this wave function of an electron, let's say. And actually, it's an interesting phenomenon. When you have a crystal lattice, the state of an electron becomes really weird. It becomes like, well, this periodicity of this lattice, it allows like very particular and very interesting types of quantum states where you would have this sort of like a wave transversing kind of the whole lattice. And that would be your electron, you know, delocalized electron, what they call. So it's kind of everywhere at the same time.
That one electron.
Yeah, even one electron. There's actually one very interesting theory, again by Feynman, and I think Wheeler also talked about that, where well, there's a hypothesis or interpretation, or I don't know, that all the electrons in the universe are just one electron. But I don't think I would be able to explain it to you now, because it's kind of, it requires looking at diagrams basically, but there is an interesting approach of that sort. Like you know, basically, you can depict, for example, antiparticles as particles moving backwards in time. It stems from that sort of reason.
All right. I've seen Feynman diagrams show those a little bit. I see.
Yeah, if you look at Feynman diagrams, you see there are arrows, and like there's some arrows kind of go forward and some kind of go backward. So the ones that go backward, these are actually antiparticles. But that's just a graphical way
models,
of
though,
depicting.
Right? Huh? It's a model. It's always the abstraction of.
Yeah. Feynman diagrams, it's actually just a graphical representation of equations, because you can unambiguously associate an element of a Feynman diagram with a term in an equation.
Right.
So
it's another way of visualizing the equation.
Yeah, exactly.
Okay. Very cool. Anyone else? Jim, what do you think? Is Jim there? Jim.
Yep, I'm here.
Yeah.
Yeah, I'm still pondering.
Okay.
Well, in a nutshell, basically, what I wanted to say is that, yeah, we have equations that seem to work, but we have no idea where they come from. And then this is a problem. Like, whenever somebody tells you that quantum mechanics explains everything, well, no, it doesn't explain anything really. Right. Like, you can just calculate some stuff, and that's it.
What's your role in oh, do we do this? Okay. Good. Like, as far as like your role in the university and research and what are your areas of focus, and what are the things that float your boat in quantum mechanics?
Oh, so I've read a lot about these problems, you know, of measurement and so on, when I was dealing with, well, basically my work, my academic work, the topic of my PhD thesis is about confinement of quarks. So these strong interactions. And what we do there is we try to utilize these quantum informational approaches to kind of explain why quarks are not observed. So we're using this concept of quantum decoherence as a way of describing why quarks are not observed, that they kind of interact with this environment of quantum fields, of fields of strong interactions, you know, the gluon fields, and they kind of lose their color because of that. And the confinement is exactly the problem of why the non-observance, so to speak, of color. And color is just a fancy term. It's just a quantum number that differ quarks and gluons actually from other particles. So that was my connection to this whole topic. Basically, quantum information. Yeah.
Right. You may have touched on this, the one that always kind of just like the fundamental naming of things, but the quanta or quantum itself, the etymology of it. And do you know the history of the naming of it?
Well, I know what quantum means in Latin, but it just means like that much.
That much, yeah, measure, count,
yeah. But do you have like a special story to share?
I mean, no, I mean it hits me as okay. We've got these discrete things that we can identify. You know, I mean, it seems to me that it's a driven by a philosophy of being able to measure.
Yeah, well, yeah, these like energy levels is definitely a big thing. It's one of the most prominent results of quantum mechanics. But I can tell you with my current experience with some of the alternative theories that they can be more or less explained by standing waves, you know, just basic electromagnetic wave, which is standing. And obviously you can have only, you know, limited amount of them, basically, which would be determined by the potential, you know, the kind of the configuration of your resonator, so to speak. It would determine what kind of standing waves are possible, and that is essentially the other way of kind of reformulating the whole problem of quantum mechanics. Because Schrodinger's equation, for example, it's exactly that. It's an equation for resonator, or something to that effect. So it's not a big wonder that you get discrete energy levels from it.
Right. Very cool. Anyone else like to ask Eugene a question?
Yeah, hey Eugene, this is Bruce. I'm kind of a simpleton when it comes to all this particle wave stuff, but when I was looking at between the Earth and the Sun, the transformer process, it seems to me that this entanglement idea is a simple induction process, possibly. What do you think about something like that? Hello?
Yeah, I'm here. Sorry. So I would say that according to quantum mechanics itself, it does not really have any physical, it does not require any physical medium, you know. It's just, again, in this sense, I kind of more or less align with this informational interpretation. I would say that indeed the state vector is more or less only our knowledge about the particle. So like it's not fundamental in that way, you know. And when we say that during teleportation the quantum state gets transferred, well, nothing physical gets transferred anyway. So no energy, no matter, no information. It's only the quantum state, which is to a large degree and a completely abstract thing, you know.
So the entanglement is not really doesn't have a physical basis. Is that what
yeah, I would say it's more of an informational phenomenon. Like we're saying that the states of two particles are correlated, but it does not mean that there is some physical connection between them, you know.
Okay.
Well, at least not necessarily so. Well, I mean, there are again different interpretations. Like some people think that it's something genuine, you know, in the sense that something really happens, and so on.
The ether, I've heard that.
Yeah.
Okay.
I don't think they like the ether too much. I don't think the ether gets to play a role there, right?
Yeah, I actually don't know what's the fuss about ether, like, because, well, if you look at the modern concept of a quantum field, it has basically all the properties of ether, like it's everywhere, and if you excite it, you get particles and so on. like even the very concept of a vacuum, like it's not emptiness, you know, the modern idea of vacuum. A vacuum is the main state of quantum fields. This is what it is. So the fields are there, it's just that they are not excited. If you pump some energy into them and they get excited, then particles appear. But a vacuum is still the presence of the fields.
If it's in a zero state, is that possible? You can describe it,
Yeah,
right?
yeah,
Then
yeah.
there's no, then there would be no particles, right? So that would be your lowest energy configuration.
Yes, exactly. And this is you probably know this, you know, 0 point energy thing. It stems from the fact that even like the quantum resonators have some energy even at the lowest possible state, you know, and that's the I mean, if you just solve Schrodinger's equation for potential well, you know, some sort of configuration of potential energy, then even there is a level below which you cannot fall, like the most like fundamental, the lowest level, but it still has some energy, you know.
Okay.
So and this is what is called 0 point energy. But the thing is that you cannot extract it in any way, you know, because again, you cannot fall lower. So you cannot take from this particle. You can only jump upwards, you know. So in a way, it's just an artifact, a mathematical artifact, because, you know, basically potential energy is you can set your zero at any value, you know.
Right.
It's kind of you can move it up and down, so it doesn't really matter in that regard.
Eugene, is it the case that matter moving through a quantum field also results in electromagnetism emerging from it? Just the actual motion and momentum causes electromagnetism to arise?
Well, the electromagnetic, I mean, again, like the most fundamental view on it currently is that there is an electromagnetic field and it's present always. So yeah, if you pump some energy in it, you excite some particles in it, which are photons. Well, then you have some fields that you can measure, you know, the electric field, magnetic field, and so on. But the field is there anyways, even if you don't excite it.
Right. So moving through it with like a particle moving through it, like photon or any particle, the faster or slower that particle moves, then obviously its magnetic moment and energy level would change relative to its velocity in the field itself, right?
To be honest, I don't get your message. Like, what do you mean?
Well, you said that the quantum field is similar to an ether field, or the same thing essentially, right? So it's always present, and it has a certain energy state. So if I imagine, just as a metaphor, a bullet, you know, magnetic, just a bullet of some sort of matter going through that field, the more energy that particle has, then the higher its energy level, and thus the higher its magnetic field and its electric charge. Like the more energy in is the same as, you know, mass is equal to light speed squared, right? The more energy, the level energy is relative to its velocity in mass.
Well, you see, the thing is that your bullet itself is just an excitation of quantum fields. So the motion of your bullet is just the propagation of this excitation from one point to the other. That's what happens. You see my point? Like, I don't know. I want to bring some analogy, but I can't, unfortunately.
That's what I'm trying to think of too, right? It's so the faster.
Well,
the faster the bullet was moving through the field, like the field is propagating the bullet, but the bullet's going through the field both at the same. It's a symbiotic type of thing, right? So the faster the bullet, the more energy in the field, right? The more energy the field is imparting on the bullet. It becomes sort of circular, but it's that deterministic thing that I struggle with, I guess.
Well, it should be. I mean, well, there is some sort of self-interaction of a field, if you like. Like there are some alternative new theories about nonlinear electromagnetism, which has a lot of potential results. I would say I'm taking a lot of interest in that currently. But anyway, so yeah, probably a good analogy for that would be like a wave on the surface of an ocean or something. So this wave, like the main state of this field would be, you know, a completely flat surface of an ocean. But if you excite it in some point, like you create a peak, you know, in height, and it might propagate on the surface. So that would be kind of more or less the analogy for the motion of a particle. So there is a kind of a field that supports it because the particle itself is a manifestation of this field, this wave on an ocean. But and it kind of propagates through the field on top of the ocean, you know.
Yeah, no, that makes sense. I sort of see things in, I like to think in three-dimensional spheres, right? I'm always doing stuff in spheres, so 3D space. I see it as like a sphere propagating through a whole bunch of packed spheres, right? And where they collide and interfere with themselves is where you get perturbations in the field, and it's like spheres within spheres. Yeah. Or a whole bunch of spheres, I guess.
That kind of sounds like a four-dimensional sphere, you know.
Yeah.
Basically, a sphere in 3 dimensions is a projection of a 4-dimensional sphere on 3 dimensions.
Right.
But it has many projections, so you can have many spheres in one sphere, so to speak.
Right.
Yeah. Very good. So what do you think? Should we call it for today? Anyone else have any more questions? Or?
I wanted to chat with you a bit, Dave.
Sure. Yeah, absolutely. You would like to do it here, or would you like to do it? I'll call you afterwards if you like, Richard. It's good. It's good to hear your voice,
yeah.
by the way.
Yeah. No, I just wanted to. I mean, it's been a long time since there have been any sessions.
Right. Yeah, it's been an interesting adventure as it has been up to this point, but there's plenty of adventure tales to share. So I'll give you a ring. But,
okay.
Yeah.
Okay. I'll be here.
Okay. Anyone else? It was a really nice meeting. We're gonna have to not do the TBD meeting tomorrow. I got something that came up, so we can reschedule it later on in the week if you like. But for tomorrow, we're going to postpone it. But thanks again, Eugene. Awesome job, man. Just going through all that stuff, and always compelling. Looking forward to more. Really enjoying the philosopher pieces that you're putting up. So.
Yeah, thanks, Eugene. Appreciate that.
Yeah.
All right. So, well, I'll send the link to this presentation to a chat.
Okay.
If you want to look at it afterwards.
I'll put this together and then render it out and get it up. It's always the upload is always a long time. So, but
yeah,
I'll try to put it together this evening and then get it up there, and so we have it to share around. So.
Yeah. Okay. So if you guys have more questions afterwards, you can ask me. And so on.